All right, so this is our new notes for today. It's not called La Hospital's rule. It actually is a French name. I don't I don't speak French, but I can at least give it a try. We say L'Hôpital's rule. L'Hôpital's. So this is L'Hôpital's rule, and for this, basically what it's doing is it's addressing a way to figure out a limit of a rational expression here, where we have some function over another function. And we've done some limits of these sorts of things before. However, there's certain limits we wouldn't have ever been able to find before that this rule is now going to allow us to do. Notice basically the big situation that this addresses, what it allows us to do is it allows us to deal with the situations where when we actually figure this out, we end up getting either 0 over 0 or infinity over infinity when we just use direct substitution at the start. So it's looking to see if we end up with 0 over 0 or infinity over negative infinity. Infinity over infinity or negative infinity over negative infinity. Then how do we get what that tells us then? And so let's actually see how we can apply that. Here's the first example that we're going to go through on this. Go ahead and write this problem down. And this set of steps really is the same set of steps that we always have to use anytime you have a problem that might even be a candidate for using L'Hôpital's rule. The first thing you do is you look to see, can we find the limit without using L'Hôpital's rule? Because if we can, well, first of all, it should make the problem a lot simpler. And as we'll actually see here in a little bit, if you try to use L'Hôpital's rule with something that doesn't even meet its requirements, it gives you some wrong answers. It gives you some misleading information. And so we always need to first see if we can find the limit by some other means. Then, step 2 there, we go ahead and we find the limit. Now, if that means using L'Hôpital's rule, use it. If not, well, then use the other method. And so we're going to do that for this problem right here. In order to do step 1 there, we are going to see if we can go ahead and find the limit without using the rule. Well, is there a way that I can just reduce this? Well, can I cancel out the x cubes? No, we can't. I got to bring that one up because there's always like one person that's like, wait, can't we just cancel those out? No, because remember I'd have to cancel it out of every single term. Could I factor it? Well, kind of. There actually is a method where we could do a little bit of factoring here, but it doesn't get too pretty. And so we're going to go ahead and see if we have to use L'Hôpital's rule then. So in order to know if we need to use it, I find the limit of the top and the bottom individually. So I'm just finding the limit as each of those approaches 1 in this case. So for that first one, if I plug 1 into the top function, that gives me 1 cubed minus 2 times 1 plus 1, which equals 0. If I plug the 1 into the bottom function here, I end up with 1 cubed, which is 1, minus 1, which also equals 0. So notice then that when I try plugging into this original function, I end up with 0 over 0. That makes this a candidate for using L'Hôpital's rule. I don't have any other way necessarily to find that limit, so yes, that is how we're going to do it here. So in order to use L'Hôpital's rule, what we're going to do is we are going to take the derivative of the top and the derivative of the bottom of this function. Now notice, I'm taking each derivative individually. This is not quotient ruled or anything like that. It's each derivative individually. So let's take the derivative of the top here. So derivative of x cubed, 3x squared, minus derivative of 2x squared, that'll give me 4x. Derivative of 1, well, of course, that's 0, so it goes away. On the bottom, derivative of x cubed is 3x squared. Derivative of the minus 1 on the bottom, that's 0, so it goes away as well. Now, I did the derivative of top and bottom. I'm still trying to figure out what the limit is as x approaches 1. So I keep that limit written there. The only time I get rid of that is when I actually use the substitution to see what this equals. Now remember at the start of this problem, I took the 1 and I plugged it in and I saw that I got 0 over 0. I now need to plug the 1 in and see what it gives me at this point. So let's just use direct substitution, plug in the 1. So that's going to give me 3 times 1, which is 3, minus 4 times 1, which is 4, over 3 times 1, which is 3. Okay, so that gives me a negative 1 over 3, so that gives me negative 1/3. That means I actually got a value out. That means this is my answer. Notice that once I plugged that 1 into the function, I didn't write limit over here. Limit is when it's still the function. Once you plug something into it, you're no longer finding out what the limit is as x approaches 1. You are actually calculating that value. Subtle difference, but notation does matter. And so this is our final answer here. We end up finding then that as x approaches 1, that we are approaching a y value of negative 1/3. The cool thing about this is it lets us find a value that we couldn't have found otherwise. Because if I take a look at the graph of this, this is zoomed in on the graph into the area that we're interested in, and we just figured out what was the limit as x approached 1. We found the value of where that hole was in the graph. A value which we couldn't have found any other way. And so it lets us find what a theoretical value would be, even though there actually isn't a value there. Being able to find out where those points are can be very useful. Alright, so for our next problem here that we're going to practice with, again we go through the same steps. Step 1, check if we can find the limit without using L'Hopital's rule. Well, that basically means going back to those old skills that we have. And in this case, do you see how actually we can simplify this rational expression before we do anything else? Because notice the bottom factors. So that means we're actually doing the limit as x approaches 2 of, well, that'd be x minus 2 over x minus 2, x plus 2. Oops. And so those x minus 2's cancel out, so really we're just doing the limit as x approaches 2 of 1 over x plus 2. Alright, let's try just plugging this 2 into the expression and see if that gives us anything. So that gives me 1 over 2 plus 2, which is 1 over 4. So that actually gave me a realistic value. That gave me something I can use. So that tells me what my answer is. It actually tells me that the limit as x approaches 2 is 1/4. And we're done. A little side note here, I kind of skipped over it, but I'm thinking I probably should go back and just mention it. I actually did start by trying to plug the 2 into the original function. I just did it so quickly that I didn't really talk about it, but I should have. Because if we start one of these problems, the easiest way to figure out a limit is just by using direct substitution. If I had plugged the 2 in at the start, and that hadn't given me something like 0 over 0 or something, like this one did, then I could just use that number. If it gave me 1/4 at the start, great, go with it. It just happens that it didn't. Okay. So we found an answer here of 1/4. Again, going and taking a look at the graph. This is what the graph of this function would have looked like. Notice what we found again was the location of that hole. We figured out that at x is 2, we have a hole up at 1/4. Alright, next one. Alright, and so with this one, let's go ahead and start by doing the direct substitution just to see if that works. Try to be a little bit more explicit about that. So if I plug 1 into the original function, on the top, that'd be 1 squared, which is 1 plus 1. And on the bottom, we do the natural log of 1. What is the natural log of 1? It is 0, yes. And so that would give me 2 over 0. But using direct substitution just gave us something a little bit odd here to work with. Because already, I know I cannot use L'Hopital's rule. We can't. Because, remember, I can only use L'Hopital's rule if my original function when I plug in just using direct substitution, either gives me 0 over 0 or infinity over infinity. I don't have that. I got 2 over 0. So what is happening here then? Well, we aren't going to get into then how would we find it. All we determined here was that we cannot use L'Hopital's rule because of that. So then if we end up where we are dividing by 0, what's it tell us is going on the graph? Well, it tells us there's an asymptote there. In this case, notice that one part of the reason why it's not giving us anything we can work with is because from the left we're approaching negative infinity and from the right we're approaching infinity. So there actually even is no limit. The limit doesn't even exist there. So again, you got to check and see, would that work? Now, little side note here. Sometimes after we've been doing these problems for a while, it's easy to just jump in and maybe try to blindly use L'Hopital's rule on this. If we had done that, we would have done the limit as x approaches 1, and we would have taken the derivative of the top and derivative of the bottom. It would have given me 2x over 1 over x, which equals 2x squared. Notice if I plug 1 into that equation, it gives me an answer of 2. Obviously, our limit here is not 2. It'd be trying to say that somehow we got our limit right there. Yeah, no. And so that's partly why we need to check and see if it actually meets the requirements of it. Because if it doesn't, it actually will give us the wrong information out. All right. So then let's take a look at this typical. We're used to saying this function all the time, right? Yeah, that's sarcasm. Yes. Go ahead and write this problem down. We'll see how we go about approaching it using L'Hopital's rule if necessary. All right, so first up, looking at this one, we can very quickly see there's not a nice, pretty easy way to simplify this, right? So we can't just find the limit by simplifying. So let's actually try just direct substitution. Let's plug in the x equals 0 and see what that gives us. So if we plug in 0, we end up doing e to the 0. What is e to the 0? 1. Yep, because anything to the power of 0 is 1. Minus 0 minus 1. So plugged in 0 on the top. Now we plug in 0 on the bottom, which means I need to do cosine of 0. What's the cosine of 0? So that gives me 1 and then minus 1. And so on the top then I end up getting a 0. On the bottom I end up getting 0. That means that this then is a candidate for using L'Hopital's rule. So let's go ahead and employ it here and see what that gives us. So remember that in order to employ L'Hopital's rule, I'm going to take the derivative of the top and the derivative of the bottom here. So on the top, derivative of e to the x, well that's just e to the x. And then the derivative of x is 1. Okay, then on the bottom, I do the derivative of cosine, which is negative sine. All right. Now let's try substituting in again. All right, plug in the 0 for x. When we do that, well, e to the 0 is still 1. So that gives me 1 minus 1 on the top. And then sine of 0. What's sine of 0? That would be 0. So that would be negative 0, which is 0. And so that equals 0 over 0. Great. We just used L'Hopital's rule, and it gave us exactly what we started with, 0 over 0 still. But because the idea behind L'Hopital's rule is that taking the derivative of a function will tell us what the limit is, I can actually keep taking the derivative over and over again until I actually get something that isn't 0 over 0. And so what we're going to do next is we're going to do the same process again. We're going to take the derivative of the top and the bottom of this function. And let's see what that gives us. We're still looking for the limit as x approaches 0. So on the top, e to the x still just gives us e to the x. The derivative of negative sine of x will be negative cosine of x. Now let's try Using substitution again, let's plug in the 0. E to the power of 0 is still 1. On the bottom, cosine of 0 is still 1. Just there it's negative cosine, so it's negative 1. Well, at least we didn't get 0 over 0 again, right? And so 1 divided by negative 1 is negative 1. That means that I've now found the answer. Negative 1 is my limit. And so in this case, we can see that if you take the derivative of top and bottom and you still end up with 0 over 0, just keep going. Keep taking the derivative of the top and bottom until you get to one that isn't 0 over 0. Or until it's clear that it's not ever going to change, because there are functions like that as well. And one last time to see what the graph looks like on that. It's a rather interesting looking graph, if you actually make it. But it's actually telling us then where that hole is again. Telling us where does that point occur. All right, you've seen a number of these done now. I think you should be able to do them on your own. So go ahead and please find this limit on your own first, and then we'll come back together and take a look and see if you got it all right. All right, and doing this problem, the very first thing that you hopefully tried was just looking to see, can I just use direct substitution at the start and just plug in the 0 for x? Well, if we do that, we end up getting 0 squared, which is 0, and on the bottom we end up doing 1 minus the cosine of 0, which is 1. So it gives us 0 over 0. Remember that it's the 0 over 0 that tells us to use L'Hopital's rule. All right, so it does tell me to use it, so now I'm going to do the limit as x approaches 0, derivative of the top, 2x, derivative of the bottom, gives me sine of x. Because the derivative of cosine is negative sine, and negative sine gives me positive sine. All right, and then once again, let's try direct substitution. Let's plug in that 0, see what it gives me. So that's going to give me 0 on the top, and on the bottom, sine of 0 is 0. Okay, so that tells me I got to do it again. So then, limit as x approaches 0, derivative of the top is 2, derivative of the bottom is cosine of x. So, if I plug in 0 for x in this case, that gives me a 2 on the top, and on the bottom, cosine of 0 is 1. Well, at least it's not 0 over 0. That tells me I've gotten to my answer. So 2 over 1 equals 2. That then is my final answer. That is my limit. So I know that as x is approaching 0, I'm getting closer to a y value of 2. And yes, if we made the graph, we'd be seeing a hole at the graph at that point there. And then this is going to be the last one we do today. In this case, we got to deal with infinity as part of the process. So go ahead and write down the problem. And then again, I start the same way I always start, which is, hey, can I just use direct substitution and make this thing work? Well, if we do that, on the top, I end up doing 2 times infinity. What does 2 times infinity equal? Infinity. Infinity is weird to work with, as you're going to be seeing here. But 2 times infinity is infinity. And infinity plus 7 is still infinity. So the top here really just equals infinity. On the bottom, infinity squared is infinity. Infinity times 3 is infinity. Infinity minus 5 is infinity. So the bottom is infinity as well. So for the first time we end up seeing a time where we need to use L'Hopital's rule, but it's because we have infinity over infinity instead of 0 over 0. Yes, we can also use it in this situation though. So that means we're going to do the limit as x approaches infinity, and we're going to take the derivative of the top, which gives me just 2, and the derivative of the bottom, which gives me 6x. And now once again, I try substituting in infinity to see what that gives me. And so when we do that, the 2 on top, well, it just has to stay at 2 because there's no x there to plug in, right? So that's a 2. And on the bottom, we do 6 times infinity. And no matter what you multiply infinity by, it can't get any bigger. It's still infinity. So we end up with 2 over infinity. Is that possible to do? Well, infinity, again, it's a weird little number. Anything times infinity is still infinity. And anything divided by infinity is 0. Because basically a way to think about it is that if you have 2 wholes and you're going to cut them up into an infinite number of pieces, again, that theoretical idea of an infinite number, how big is each piece? Well, they're going to be super, super tiny, right? So close to 0 that they basically are 0. Just like infinity is getting insanely large as well, to the point where it's beyond any actual representation other than just as infinity. So dividing by infinity gives us 0. This then actually is the limit, which you might have already known when I first put up the problem. Because way back in Unit 2, I gave you problems that looked like this then. And we were able to figure out what that limit was because, remember, we had that whole thing about, well, is it top heavy, bottom heavy, or is it balanced? And we could figure out where the asymptote was based on if it was top heavy, bottom heavy, or balanced. This one, notice it's bottom heavy. And you may recall that if it was bottom heavy, we found that the graph had a horizontal asymptote at 0. And so that as x approached infinity, y approached 0. Well, we just basically used L'Hopital's rule to prove that and to show in a different way how we can know it.